Oh, I love that. I love it when you say good morning back. Then I feel welcomed. That's the best. You can make your way to your seats. We're going to get started. I'm so honored and happy to welcome you to Family Day at HSG 2024. My name is Janine Mercandetti. I am the Senior Manager of Contracts and Projects with the Huntington Study Group, and I'm honored to serve as your MC for Family Day. Yeah, all right, I'll take it. I like to start a Saturday with a nice round of applause. I'll take that. Before we formally kick off Family Day, I'd just like to call your attention to a few very quick housekeeping items. Today's events are scheduled until 4 o'clock this afternoon with an Ask the Experts panel and dessert social. A buffet lunch will be available at 12 o'clock out in the main foyer, which is right outside these doors. And we invite you to visit the exhibitor tables, which are also located in the main foyer right outside these doors. Thank you, everyone. And now I'd like to please welcome your Family Day hosts, Dr. Martha Nance, longtime chair of the Family Education Committee for the HSG, and Dr. Andrew Duker, your hometown hero from the University of Cincinnati. That's right. They're going to welcome you to Family Day.
All right, I've been given the task of going first, so bear with me. Oh my gosh, this is amazing. It is so great to see all of you here today. Welcome to Family Day. We here at Cincinnati are so excited to host the Huntington Study Group Family Day here in Cincinnati. I'm Andy Duker. I'm the director of the HDSA Center of Excellence at the UC Gardner Neuroscience Institute. I want to thank my friend and colleague, Martha Nance, and the whole Family Day Planning Committee for putting together an incredible day of education, of learning and sharing, and of community. Huntington's disease touches the lives of everyone in this room in a different way, but we're all here today because we care about making people's lives better today and about making the future better for people with HD. Just a little bit about Martha, because she may not tell you, but she is amazing. She is the director of the Huntington's Clinic at the Hennepin County Medical Center in Minneapolis, and she's a neurologist at the Park Nicollet Clinic in Minnesota as well, and directs the Parkinson's Center there. She's trained in neurology and genetics, and she has a special place in her heart for everyone who deals with Huntington's disease, as we all do. Just a few days ago, she received the Lifetime Achievement Award from HSG for the work that she has done and continues to do. So I can't think of a better person to help direct this day. When I started fellowship in movement disorders here in Cincinnati in 2005, I had the opportunity to learn from incredible mentors like Dr. Freddie Revia, who's here today, who opened my eyes to the world of Huntington's disease and helped me to fall in love with the field. It's been an honor to contribute and now to direct the Huntington Center here in Cincinnati, to be able to provide comprehensive and multidisciplinary care with physical therapy, occupational therapy, speech therapy, psychiatry, neuropsychology, genetic counseling, social work, and so many other resources for our patients. We've been able to add integrative medicine, massage therapy, Tai Chi, art therapy, even a video game clinic. But ultimately, the most important ingredient in our HD clinic is you, the people, the families, the patients, and the friends affected by Huntington's disease. So you are what makes this center so strong, and it warms our hearts to see all of you here today. Thank you for being here and for giving up part of your Saturday to learn how we can live better with Huntington's disease. And with that, I will turn it over to Martha.
Thank you. I have very few words of introduction, and then I'll launch into the first presentation of the day. Just a little bit about the Huntington Study Group, who is the group that is organizing and hosting this Family Day. Huntington Study Group has been in existence for 30 years, ever since the discovery of the gene. It is a consortium of clinical centers doing clinical research in Huntington's disease. We're in a period of change in the Huntington Study Group. Our longtime leader, Ira Scholson, who founded the organization, died earlier this year. and we still grieve his loss. Most of us in the Huntington's disease field are the professional children or grandchildren or siblings or cousins of Ira Scholson. We have a new leader of the Huntington Study Group, Dr. Daniel Clausen, who's from Vanderbilt University. And we're looking forward to, Daniel has all kinds of ideas about really moving the Huntington Study Group forward more quickly. It all requires all of us. We're not going to get an answer without all of us working together to find better treatments. Researchers can't get better treatments without people who have Huntington's disease. People who have Huntington's disease can't get better treatments without the researchers. So let's work together. And it really is wonderful to have so many people in the room so we can build that connection. How many people are here from Ohio? You're really quiet, you Ohioans. Anybody proud to be here from Ohio? No. Whew. Okay, good. I got one little hoop. Anybody not here because they're at the Ohio State game instead? They're quiet too. How many people are not from Ohio? All right, so we got kind of a 50-50. We'll have fisticuffs later in the day. So, all right. Well, let me start with my presentation, which hopefully somebody can pull up on the slides. I don't know. So my presentation is entitled Demystifying HG Science, or HG Research. I forget what I put on the title. And it's my attempt to, then I can't see the slides at all. Great. So it's my attempt to try and explain research in English. We're pretty heavy on the research talks today, and there's a reason for that. You have the world-leading researchers here in this hotel this week, and we really want to take advantage of that. To have a presentation that's a little heavier loaded on research than you might have at a regular state family education day. But let me just try to introduce you to research in a more family-friendly way to make it easier to get through the rest of the day. We're always supposed to put our disclaimers. These are some of the things that I do and hats that I wear. What are the goals of Huntington's research? Well, our mantra from Ira Scholson was always that we wanted to develop treatments that make a difference for people impacted by Huntington's disease. And that can include treating symptoms. It could include anything that makes life better. But the things we're really hoping to do at some point is to slow the course of the disease, or stop or reverse the disease, or maybe even prevent the disease. So how do we go about doing that? There are some advantages to studying Huntington's disease and some disadvantages. The advantages we have compared with similar diseases like Parkinson's and Alzheimer's are that everyone with Huntington's disease has the same root cause, this CAG repeat expansion in the HTT gene. By the way, E.J. Garner, raise your hand, is her job today is to ding the bell if anybody up at the front of the room starts saying words that nobody understands. So, so if you hear the bell ring, yeah. But we'll talk about CAG repeat expansions in the HTT gene in a minute. So, so therefore, we have the ability to know ahead of time who will get Huntington's disease in the future. And you cannot say that for Parkinson's or Alzheimer's. I cannot look around the room and know who's going to get Parkinson's. But we could, whether you should or not is another question, but we could look around the room, essentially, and know who is and who is not going to get Huntington's disease. And that allows us to do research to really study the earliest changes in the brain before somebody has overt symptoms. We have an engaged, interested patient and family community. Give yourselves a round of applause. Engaged families. And we actually have a more or less coordinated global research community. So the Huntington Study Group includes not only something like 90 sites in the US, but also Canada, Australia. Some of our European colleagues come over, and some of us go to the European HD network meeting, which this year was in Strasbourg, and their next one is in Krakow, Poland. So, we get trips to obscure places if you go to the European group meeting. So we all are really trying to work together to solve Huntington's. Challenges in the Huntington's research world are relatively small number of people. There's 3 million people in the country with Alzheimer's and 1 million people in the country with Parkinson's and 30 or 40,000, maybe 50,000 with Huntington's. The course of the disease is long and slow, and that's really hard for the getting funding to do a study if it's going to take 10 years to show whether your treatment has made a difference. That's too long for funders and for impatient patients, families, and researchers. It's also hard to access the body part that is most affected by HD. It's pretty easy to study blood diseases or skin diseases, even liver diseases or bone diseases, but people don't really like to give you little chunks of brain tissue to look at on an annual basis. So we have to use creative ways to try and understand Huntington's disease. So here's your genetics lecture. So just to get us all on the same page, how many people ever took a genetics class? Holy smokes. How many, well, okay, wow. So you guys, all you who took this class could give this lecture, but we'll review it anyway. So there's something like 30 trillion cells in your body. Each cell contains 30,000 pairs of genes that are packed into 23 pairs of chromosomes inside the center part, the nucleus of each cell. The reason these things come in pairs is because you get one complete set of chromosomes, genes from mom, and one complete set from dad. When the sperm and the egg fuse together, then you have two complete sets. And each gene contains 300 to 300,000 or more three-letter DNA words in the recipe that it is describing. So a gene is basically a recipe to tell your cell how to make a particular chemical. And the gene language only has 4 letters, A, C, G, and T. So, geez, what could go wrong if you have 30 trillion cells with 30,000 genes, each of which has 30,000 letters in it? What could go wrong? Well, it turns out that in Huntington's disease, the only change in the gene, in the HTT, we sometimes call it the Huntington gene, the only variation in that gene that leads to Huntington's is called a CAG repeat expansion. So if you look over on the right side of the slide, I drew a picture of a cell and the nucleus and the chromosomes. Those are all things you can see if you look under a microscope. What you can't see are the genes that are sort of lined up along the chromosomes. And so I have a diagram of 2 chromosomes that each have 6 genes, one of which is the Huntington gene. And if you read the Huntington gene, it might read, as it does at the bottom on the right, TGC, CCC, CAG, 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 CAA, CAG. And if you look at the one below, it has 2 more, that has that word CAG repeated 2 more times in a row. So it's got more CAG repeats. There's a lot of variation in the normal number of CAG repeats in this particular gene. Anything from 10 to 35 is normal. Anything that's 36 and above is not normal and can lead to Huntington's disease. And there's a couple shades of gray. We're used to thinking of genes as being black and white. Either it's normal or it's not normal. But there's a couple little shades of gray in this. So repeat numbers of 36 to 39, low in that abnormal range, can cause Huntington's, but may or may not lead to symptoms within a normal life expectancy. So I had one guy who's 92 years old and had 37 repeats, waiting for something to happen. And the other sort of shade of gray, there's a doctor word for this, may cause the disease, but not always. We call that reduced penetrance. It's like that abnormal gene can't sort of penetrate hard enough to actually cause a disease. And then CAG numbers in the high normal range, say 27 to 35, are not going to make that person, if you have a repeat number of 34, that's not going to cause Huntington's disease. But the repeat number, when it passes from parent to child, sometimes gets bigger. And so a parent with 34 repeats may have a child with 37. The genetics word for that is meiotic instability. So if you memorize all these words, you can impress your friends at your next party. So the repeat number, especially when it gets into that abnormal range, the repeat number tends to get bigger as it passes from parent to child, but it can get smaller. So how do you use a gene to make a protein? Well, there's your cell. There's the nucleus. You can think of the cell as being the house. You can think of the nucleus as being the library. And then you have another structure called the ribosome, which you can think of as being the kitchen. So there's the two chromosomes. The blue one now is the one that's got too many CAG repeats in it, or it's really not the chromosome, it's the gene. I haven't included the whole chromosome, but the blue one is the abnormal Huntington gene, and the red one now is the normal one. The recipe books, the chromosomes, the genes sit in the library. How many people cook chocolate chip cookies in the library? No, where do you cook chocolate chip cookies? In the kitchen. So, but you can't take these books out of the library. So how are you going to get that recipe to the kitchen? You make a Xerox copy, okay? That's called mRNA. So now you see the mRNA copies of both of those genes, the normal red one and the not normal blue one, and those mRNA copies physically go to the kitchen, where they are used to make to generate the Huntington protein. Or if it was my recipe book in my kitchen, it would be chocolate chip cookies. And so here comes the not normal mRNA also going to the ribosome, making a not normal protein that it's too big. Does that make sense? So now you've made an abnormal Huntington protein, or we often call it the HTT protein. How does that cause Huntington's disease? Well, maybe it doesn't do its job, whatever that is, efficiently or effectively. Maybe it does things it shouldn't do. Maybe like my chocolate chip cookies. Have you ever tried to put 43 chocolate chip cookies into a cookie? You end up with a chocolate mess that kind of crumbles and clogs up the oven, burns on the side of the oven. So maybe that HTT protein that's too big sort of crumbles and falls apart and clutters up the cell. Maybe one thing leads to another. But at first you might want to say, well, what does the HTT protein do? And this is where I'm going to dive into an analogy. It's going to take me 5 minutes, bear with me, but it helps to explain Huntington's research. I'm going to talk about a different gene product that came to be in Minnesota that we refer to as the MATT gene product. Sometimes we call it MAT. And you could ask, just like, what does the HTT protein do? What does the MATT protein do? Well, the MAT played saxophone, and good soccer player, and really good student. So exactly what this MATT gene product did might depend on what time of day it was, who he was with, where he was. And similarly, exactly what the HTT protein does may depend on what time of day it is and how old the person is and what cell it finds itself in. But the other thing that the MATT gene product did is like to play video games. And who knew, looking at this gene product, that it actually carried, anybody know what that is? World of Warcraft, yay, one person in the room knew. So I gave this talk to the HSG youth organization, and they all knew what that was. So this poor gene product had the World of Warcraft mutation. We sometimes call it the WoW mutation. Now, symptoms of the WOW mutation do not develop until you're about 15. But once the symptoms begin, there are all sorts of things that happen. The bizarre sleep patterns, like, up till 5 in the morning and sleeping till noon. Fewer vowels on the report card, so those A's turn into B and K and D. And the saxophone becomes dusty, and cans and candy wrappers accumulate, and dirty clothes are in a heap, and after a while, clean clothes end up in the dirty clothes pile. So there were 2 researchers in Minnesota that were particularly interested in understanding this WOW mutation and finding a solution to it. So what did they do? Well, so the first thing they did was send out a survey. They asked everybody they knew that had a WOW mutation some questions about symptoms. And it turned out not everybody with the WOW mutation owned a saxophone, but everyone who did own a saxophone, the saxophone was dusty. And so that led to the first idea how to treat the WOW mutation: dust off the saxophone. And it didn't work. So one of the things that researchers do once they identify a disease entity is to do surveys, to do observational studies, to look at as many people as possible who have this condition, to see which things that are going on are due to the condition and which things are just unique to that person. There are several currently running HG studies, and many of them are available in the booths outside that are sort of observational or survey kind of studies. My HD History, Join HD for kids, Change HD, Enroll HD. How many people here are enrolled in Enroll HD? How many people have participated in any other study ever? Yay! How many people would like to participate in a research study but haven't yet? Yeah, that's okay. So this is our first approach to solving the WOW mutation, and it turned out it didn't work. So then they said, well, the next thing that happened is there's mice and ants and stuff, and then they're gnawing through other things and elsewhere in the house. So let's try removing the cans and the candy wrappers and see if that'll solve the WOW mutation. And that helped. It turned out that there was less additional damage in the house. So you call it working, and the ants go away, and the mice go away, but it didn't change the fact that there were video games being played until the wee hours of the morning and lousy grades on the report card. So this is the idea of treating what I would refer to as downstream effects. So a downstream effect of the WOW mutation is clothes heaping up and cans and candy wrappers. I have spent my career treating downstream effects of the Huntington mutation. So that would include things like inflammation. If you have cells damaged in the brain, pretty soon come in the inflammatory cells to clean up the damage. If you have a damage to a cell in the brain, then pretty soon the mitochondria, the furnaces inside the cells, end up working overtime to try and fix the damage. Oxidative damage. Whenever a scientist uses the word oxidative, just substitute the word rust. Okay, so oxidative damage to the brain cells, you can imagine that if you have rust in the brain, it's not going to be so good, and you might use rust protectant. This is what I've spent my career doing. And some of these things help a little bit, but they don't change the underlying HD mutation and the progression of the disease. So what about removing dirty clothes? So, again, same idea, downstream effect, and at least then the poor kid had clean clothes to wear to school. That's the idea that has led to some success in the Alzheimer's world, finally. If you suck out the bad proteins that are clogging up the cell, then might that actually help the brain to work better? And there are people starting to think about, can you use sort of an anti-Huntington antibody? Hasn't come to fruition yet. Then they tried throwing the computer out the window, and that worked, no more World of Warcraft, but it had undesirable side effects. So the poor kid couldn't do his report for school. And that might be sort of analogous to the Roche trial of tominersen that was terminated in 2021 because it seemed like it was too strong. The people that received the real drug were getting worse or quicker. It was causing more harm than good. So these are all the things the researchers tried. So what happened next was that the MATT gene product moved somewhere else, and the researchers no longer had daily in-person contact. Instead, that changed to sort of weekly, or I don't know, maybe it was sort of monthly, and then pretty soon 3-monthly phone contact. And so you talk to the research subject, and the research subject says, "Oh yes, everything's fine." And so the researchers are happy and think that the problem has been solved. Well, maybe not. It was maybe a couple, 3 years ago that the researchers learned that the World of Warcraft mutation had not gone away. But what happened was the entry of a certain form of gene therapy that was not even the idea of the researchers, it was kind of the idea of the research subject himself, which we refer to as the Clara gene product entered into his life. So this form of gene therapy seemed to solve this World of Warcraft problem. Interestingly, it didn't solve the sleep disorder. So now we still have to think that maybe the World of Warcraft mutation doesn't cause the sleep disorder. Maybe the sleep disorder is separate, and maybe it leads to a higher risk of having the WOW mutation. So what did we learn from all this? So number one, association is not causation. So dusty saxophones do not cause the problem. And maybe the sleep disorder isn't actually caused by the WOW mutation. Normal cell products can get sort of caught up in the mess, so the clean socks get stuck in the dirty clothes pile, and we think that may happen in Huntington's, that the Huntington protein kind of accumulates in the cell, and pretty soon normal proteins get tied up in this pile of trash, and then you have a cell that's really sick. Treating downstream symptoms might help a little bit, but doesn't really solve the underlying problem. And then loss to follow-up, there's a reason researchers want to see people in person. We're trying to train ourselves to allow video visits, but some of us are slow to move to that, and we really are even less happy with just a phone call. Yes, I'm fine. So loss to follow-up can kind of skew your impression, your results. And the final thing, honestly, is don't lose hope. There was a time when the WOW mutation researchers had kind of lost hope. This has been going on for 20 years, and it was only in the last year or so that this gene therapy entered the picture and seemed to work. So never lose hope. So lots of ideas how to treat HG, address downstream effects, prevent that recipe, that abnormal recipe from being used, keep that abnormal protein from collecting in the cell. How about just cut out the abnormal gene? Replace cells that are not working or are gone, and then treating symptoms. I mentioned observational studies already. As I said, have spent my career studying downstream effects, inflammation, several trials that I list here, mitochondrial dysfunction, oxidative damage, whatever sigma-1 receptor stimulation is or does. And then we get to these gene silencing techniques. So this is also something for you to have some idea, because many of our studies, God, we were bombarded with more companies wanting to do different approaches to gene silencing, or what we usually refer to as Huntington lowering. So there's your cell, there's your nucleus, there's the ribosome, there's the two genes, there's the mRNA, and there's the normal one turning into the protein. Good. And the idea of Huntington lowering is to inject into the cell these black things that are either called ASOs or siRNAs or microRNAs. But the idea is to put these things into the cell, that recognize and stick to the abnormal Huntington mRNA and then prevent it from getting to the ribosome. Wouldn't that be a solution to Huntington's? If you can turn off that abnormal gene and only use the normal gene to make Huntington protein, that ought to work. So you can imagine why there are many companies getting into this idea. The first approach, that the Roche trial kind of had the lead, and this was 3 years ago now, so many people know that that study was terminated because the people getting the high dose of the real drug got worse or more quickly than the people getting placebo injections. There was a second trial by a company called Wave that couldn't show that their product actually had any effect. To their credit, both companies are still heavily in the game, and both companies have new studies going on with refined ASOs that we'll try again and see if either treating people earlier in the disease works better, maybe not giving such a high dose. One of the challenges is, how do you deliver this drug to the part of the brain you want to get it to? And the two leading strategies are by a spinal injection. How often do you give the injection? That's being studied in some of these studies. Or directly injecting the siRNA into the brain. One and done. Just have a surgical injection and no more, visits to the clinic. How well do these drugs actually get into the nerve cells? How far do you want to reduce that Huntington? Maybe you don't really want to eliminate Huntington protein entirely. And how do you create one of these little black things that only recognizes the abnormal mRNA without recognizing also the normal mRNA, since the only difference is one of them has 5 more CAG repeats. So several of the companies have developed drugs that actually turn off both copies of the gene. Is that okay? Is it not okay? How much do you want to turn it down? What if your thing isn't perfect? What if it doesn't turn it down 100%? Is 80% good enough? 60%? So these are all the questions we're trying to answer with these studies. The Wave product is supposed to be, they call it allele selective, meaning that it does only recognize the blue mRNA and not the red one. That only recognizes the abnormal, but not the normal. So the Wave product is a little bit different than the Roche product because it does seem to only recognize the abnormal gene. So this is just a listing of some of these trials. Unicure has a study ongoing of a surgical injection of the molecule into the brain. Spark is another company that's starting up on a similar surgical injection. Roche, the tominersen, now has another trial called Generation HD2, and then Wave is also back in the business. And I bet you they all have booths out in the front there. The other thing is interesting, and women will relate to this, and maybe some men. If you ever read a magazine, like a food magazine, and it's got a recipe that starts on page 3, and then it says continued on page 106, and then you have to page through 100 pages of advertising and other articles to get to where that recipe is continued. What you really want to do and believe it or not, your cells do the same thing. You've got part of the recipe here, and then you've got blah, 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 then you have the next part of the recipe, and then blah, 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 blah. And the cell has to splice the relevant parts of the recipe together. And if you can screw up that splicing process, so if you've got part of the recipe on page 3 and then you have advertising at the bottom of page 3, well, if you Xerox that whole page and then tack on the rest of the recipe, you've got this gobbledygook in between. Your cell knows how to splice out that advertising and put the two pieces of the recipe together. If you can screw up that process, then you might be able to turn off the abnormal Huntington gene. How do you make that unique to just the Huntington gene? And can you make it unique to just the abnormal Huntington gene and not interfere with the normal one? But there are several companies also looking at these RNA splicing treatments, which conveniently, as somebody said at a meeting, are oral molecules. And they got a ding for oral molecules. Pill! Oral molecule means pill. Wouldn't it be nice to just take a pill to treat your Huntington's disease rather than having injections or brain surgeries? So treating symptoms, again, I've spent my career doing this as well. Tetrabenazine, deuterated tetrabenazine, valbenazine. These are 3 drugs that are FDA approved to treat chorea in Huntington's disease. How about a round of applause? There are no treatments available to treat cognitive change in Huntington's disease, but a company called Sage is working on that. So there's currently a drug in trial for cognition, specifically in HD. And then I dug up, when I was preparing for this, I dug up a couple of papers about transcranial brain stimulation, whether that's electrical or magnetic stimulation to treat cognitive or behavioral symptoms. We've been doing deep brain stimulation in Parkinson's for many years, and people are saying, again, surgery, invasive, batteries, how about we just put a little thing on, and there's other ways to stimulate besides electrical, how about magnetic stimulation, being looked at for a lot of different things, particularly in psychiatry, and why not also in Huntington's disease to treat cognitive or mood symptoms. The latest thing in our meeting, so all the talks that weren't about injecting gene therapies into the brain, we're talking about DNA repair genes. So I mentioned earlier meiotic instability, the tendency of your CAG repeat number to get bigger as it passes from parent to child. But for years, we have always said, if you have a gene test at age 10, and your results show that you've got 17 and 44 repeats, I'm sorry, you will someday get HD. If you repeat that test when you're 30 years old, 50 years old, 70 years old, 90 years old, you'll still have 17 and 44. The repeat number in your cells, in your body, doesn't change. Or does it? It turns out that in the brain cells that are particularly susceptible to damage in Huntington's disease, it seems that the repeat number starts to get bigger as time goes on, and that tendency for the repeat number in your brain cells to get bigger is mediated by certain chemicals in the body that we refer to as DNA repair genes. And there's a whole new school of thought that hasn't, it's budding, but it hasn't blossomed yet. It's not in the clinic, but it's the idea of can we impact on these DNA repair genes to keep that increase in repeat number from continuing to happen. Because there's a thought that you start to get HD symptoms when the repeat number in your brain cells gets to a certain point. And people argue about what point. Is it 50 repeats? Is it 80? Is it 100? Is it 150? Whatever number, let's say it's 100. Obviously, if you have 40 repeats, you're farther away from 100 than if you have 60 repeats. So you're closer to that threshold the higher your repeat number is, and therefore going to tend to have an earlier onset. But can we modify these DNA repair genes so that nobody ever gets to 100? That if your repeat number is 44, it just camps out there at 44 in your brain cells your whole life. Wouldn't that be nice? An area of active, really active work in Huntington's that has not come to the clinic yet. You got to be careful about fiddling with your DNA repair genes because DNA repair genes is what keeps you from getting cancer when you go outside in the sun. So you don't really want to trade Huntington's for cancer. So really fascinating area that stay tuned. What's a CAP score? Anybody know what their CAP score is? One person in the room knows their CAP score. Oh, 2 people, 3 people, all right. So the CAP score is something we invented a few years ago that we think sort of is a marker for how long you've been exposed to this too much CAG repeats. So it's the CAG age product, but But of course, scientists can't ever make anything simple, so it's not just I have 43 repeats and I'm 40 years old, so let's make it easy. I have 40 repeats and I'm 40 years old, so my CAP score is 1,600. Oh no, you have to, do fiddling with it. So, and unfortunately, there's different researchers have come up with different versions of a CAP score. But the important thing is that some of these research studies are starting to incorporate your CAP score as a way to determine whether you might be eligible for a trial at a point in your life when you're not yet overtly symptomatic, diagnosed with HD. So if you're 20 years old and want to be in a research study, you may not be scheduled to develop symptoms of HD till you're 50. Well, that's not going to be very helpful in a research trial because we have to wait 30 years or 40 years to see if we delayed your onset. But if you're 40 years old and you have 50 CAG repeats, you might be closer to the expected age of onset. And so the CAP score sort of helps us to think about what your expected age of onset might be. So you can see down there are two different versions of the CAP score, age times CAG minus 33.66. So let's just say you have 43 CAG repeats. 43 minus 33 is 10. So if you're 40 years old and you have 43 repeats, your CAP score would be 400, or roughly. And we sort of expect HD maybe to be diagnosed when you're in the 450, 500 range using that version of the CAP score. Roche is using that in their current trial. The other version of a CAP score, they've tried to get it to where 100 would sort of be the age you might expect to get HD. So that's age times CAG minus 30 divided by 6.49. So again, if you have 43 CAG repeats, 43 minus 30 is 13, divided by 6.5 is 2. And so 40 times 2 is 80. If I did my math right. So you can figure out what your own CAP score is, if you can do multiply and subtract and so on. So that's just a concept to be aware of. What about CRISPR? Anybody ever heard of CRISPR? Yes, everybody's heard of CRISPR. CRISPR is not in the clinic yet, okay? But it's another whole huge exciting area. If you ask any 8-year-old how to treat Huntington's, they would say, can't you just cut out the abnormal gene? And you pat them on the head and you say, yes, but how would you get, you'd have to get very tiny scissors and you have to put them into every cell in your brain to cut out the abnormal gene, and it's just not going to work. Well, CRISPR is little tiny scissors. So there's your cell and your gene, and here's CRISPR, snip. So now you snip that piece that you don't like, and then you bring the needle and thread to sew it back in place, okay? So that quite literally is what CRISPR-Cas9 is all about. And do you really need to cut out the gene, or could you just cut out a couple of CAG repeats? Or, there are all kinds of creative ideas that people have about how to use CRISPR to fiddle with the gene so that it is no longer going to cause this abnormally elongated protein. Same challenges that we have with the other forms of gene therapy. How do you get this thing into the cell, the brain cells? How do you get it to behave so it only does things to the gene of interest and doesn't have off-target effects affecting other genes? Working on it, not in the clinic yet. So the other thing I want to talk about is this thing called the integrated staging system for Huntington's. So way back in 1981, when I was, starting, as a neurologist, you just didn't see people unless they had symptoms. And then they would march through the stages of HD, stage 1, 2, 3, 4, 5. And the staging system we used was devised by our mentor, Ira Scholson, called the Scholson-Fahn staging system. Then in 1993, we found the gene, and that added another sort of layer on top of this. You have symptomatic people, but then you also have people that are gene positive, but not having symptoms yet. The ability to do that gene test allowed these humongous observational studies to begin. Predict HD, Pharos, Cohort, Track HD, and now those have all been replaced by Enroll HD. And and these, again, I spent my career doing this. This is what we've been doing for the last 24 years, is these kind of studies. And we finally accrued enough information to help us develop a new staging system for Huntington's disease that's to be used for research purposes, okay? So in this system, stage 0 is somebody who knows they've got the abnormal gene, but they have absolutely nothing wrong with them by any means we can measure. We do think the first thing that we can tell that's different is that if you do research level MRI scans where they have 3-dimensional measurement of the structures in the brain, the caudate nucleus begins to shrink years before a person is diagnosable. That would be stage 1. And then if you do Enroll HD, we do some fancy little cognitive tests like, listing words that start with the letter F, or doing the Stroop test where you have to read colors and the names of the colors and all. So the minute you're a little bit off on that, but not yet failing at work, not yet having chorea, but just subtle changes on these little cognitive tests, that might be a stage 2. Or maybe just subtle twitches that really don't add up to chorea yet. So that'd be a stage 2. And then the stage 3 is when you actually have diagnosable HD. So how do you layer that on the old staging system? So the ISS, Integrated Staging System, stage 0 is somebody who's completely normal by any way you want to look. Stage 1 is somebody who has probably this slight MRI change, but nothing going on their clinical exam. Stage 2 is just these sort of subtle features, but not diagnosable, no functional disability. And then ISS stage 3 begins when somebody is diagnosable. And so there's going to be a little confusion as people say, what stage are you in? And you say, well, I'm stage 2. Well, is that ISS stage 2 or is that Scholz-Fahn stage 2? ISS stage 2 is somebody who's not been diagnosed with Huntington's disease yet, but has maybe subtle changes of some type on some research test. Scholz-Fahn stage 2 is somebody who's been diagnosed and is having a little trouble at work or driving or things like that. Does that make sense to you guys? So understand that we now have these sort of 2 different stages. The one we still use in clinic for patients with Huntington's disease is the Scholz-Fahn 1, 2, 3, 4, 5. But if you're thinking about enrolling in a research study, they may be talking about this ISS stage 1 or 2. So, does that help? Does that help demystify research a little bit?